Hi everyone. As part of our last video of this series, we are automating the EDA tool with help of some extra features that can be really useful for your EDA process and accelerate your journey. What are the three features that we have added to our already done EDA process? First is the outlier analysis done using Boxplot method and Winsorization. Second is the bivariate analysis, which is creating and visualizing crosstabs for the categorical variables. And feature three is the estimation of the correlation of the numerical variables in our dataset. To talk about feature one, we have Kaviya with us.
So we have come up with an idea of analyzing the outliers with the Boxplot method and Winsorization. As you know, outlier can be problematic for many of the statistical tests, as it can mislead the information or distort the real test, or it can also make to miss the significant findings. So removing outliers is not a solution, as it would degrade the quality of the data. So here we are treating the outliers with two methods, that is Boxplot method and Winsorization. The first is I am creating a copy of the data frame where I am storing it in df cap1 and cap2. And the first method is Boxplot method. Here I have created a function which has two arguments, which is the entire data set, and also I have used an argument called as factors, which would be explained later in this function. I'm separating all the numerical variables to a data frame called as numdef. And for each of the column in numdef, I'm plotting a box plot just to analyze the distribution of the data. After that, I am finding the Q1 for this column, which is the 25th percentile. And following that, I am finding Q3, which is the 75th percentile. With Q3 and Q1, I am calculating the interquartile range, which is Q3 minus Q1. After we find the interquartile range, we are supposed to calculate the lower whisker and the upper whisker, which is given by this formula. So the lower whisker is Q1 minus the interquartile range into the factor that you given your argument, and for upper whisker it is Q3 plus your interquartile range into the factor that you given your argument. This can be better visualized with a picture. Yeah. As you see here also we have used a factor of 1.5 and we have the interquartile range. So anything less than the lower whisker is also considered to be an outlier here, and anything beyond your upper whisker is considered to be your outlier. So our objective is to cap these outliers within your lower whisker and upper whisker. So for that, the piece of code which we have written here is that, and yeah, we are printing the lower whisker and the upper whisker value. Following that, we are also printing the number of outliers for each column. As I was saying, we are capping the outlier using this piece of code. This is that when the particular value is greater than your upper whisker, replace the value with the upper whisker. If not, check if the value is lesser than the lower whisker. If it is, replace the value with the lower whisker. If not, retain the value. So this is how we cap the outliers using Boxplot method. And after you have capped the outliers, we are again visualizing using Boxplot. Now let's see the output of this function. Here we have used cars data. And here, if you see for the horsepower column, the upper and the lower whisker is 21 and 183. And here we have 23 outliers for a factor of 1.5. And before capping of outliers, you could see some of the outliers are present above the upper whisker. And after capping the output, you can see how the horsepower data has been changed. So this is how you treat the outliers using Boxplot method. Now let us see how you treat the outliers using percentile, which is also called as Winsorization method. Here I have created a function called as Winsorize, where I am passing the entire data and I am setting up the lower and the upper limit. So what is the lower and the upper limit? How can you cap using the percentiles? This can be better analyzed using a picture. Yeah. So this 10% of the data which falls at the lower end contains a number of outliers, And also the 10% of the data which falls at the higher extreme are also considered as the outliers. So I set up the lower limit as 0.10 percentile and the higher limit as also 0.10 percentile, which says that we are mentorizing at 80% of the data. Let's see how this can be implemented. Yeah. So we will be passing the arguments for upper and the lower limit. As we did earlier, we are separating the numerical data, and for every column in the numerical data, we are plotting the box plot. So the logic in Winsorization is that for the percentile which is given in the lower limit, we will find the value and we will store it as the lower bound. And for upper bound, we will use the value of the percentile which is present as 1 minus the upper limit, since it is the higher extreme. After we obtain the lower and the upper bound, we print those values and calculate the number of outliers in that column. So we use the same logic as we used before. So any value which is greater than the upper bound, replace it with the upper bound value. If not, check if it is lesser than the lower bound, replace it with the lower bound. If not, retain the value. And after you cap it with the percentile, you plot the box plot. Now let's see what is the output for this function. Here, box plot may not be a accurate representation as you are capping only with the percentile you give and not with the IRQ of box plot. But you can see that the outliers are treated and the outliers are removed in this horsepower. So that is the treatment of outliers with the box plot and Winsorization method. Now Shivani will take us to the next features.
Coming to the bivariate analysis, it is really important for us to categorize and visualize the categorical variables. We have given the power to the user to input any two categorical variables from our data set and then help in its visualization using a crosstab. So for that, we have created a function crosstab. And then we are finding the numerical and the categorical data frame and putting it in a list so that it's visible to the user. Then the same things, we are doing it without list. Then we are giving the choice to the user to input any two of the categorical variables from the categorical data frame for which they want to find the relationship. Thus, then we are finding the crosstab between the two inputted variables. And then we are plotting that crosstab with a bar plot. Let's see how the output looks. The categorical fields are just two. So I'll write one as the first column that we want to find the relationship for, and two for the second column. But using this, you can see that there are 73 cars of made in Europe, 79 in Japan, 254 in US. But there are so many different origins, so many different car models. As there are 407 distinct car models, you can see that its visualization is not that clear and it's getting so crowded. For that, we have read another data set, which is the attrition data set. To explain the attrition data set, it is a data set which talks about the people leaving or staying at the firm, and it has 20 fields. There are so many fields such as business travel, department, education, environment, its gender, job involvement, job level, etc. So there are 20 fields and close to 1400 records. As you can see, the text fields such as business travel, department, education fields are categorical variables. So let us find its crosstab and look at its visualization. I would like to see the visualization between business travel and department. So I'll write 1 and 2. As you can see, the fields did not have too many distinct values, so thus the visualization is clear. This feature can really help us in finding the relationship between the two categorical variables and thus visualize it better. Moving on to our last and the third feature, which would make our analysis even more interesting, is finding the correlation and then plotting it using a heat map, where the different colors of the correlation matrix would tell you if it is more correlated or if it is less correlated. So for that, we have made a correlation function. In that correlation, we have done it for just the numerical variables. So we have found out the numerical data frame, which includes just the numerical fields of our data set. And then we have made a correlation matrix and then have found rounded the decimals to 2 digits. We have thus plotted the correlation matrix using the heat map operation. As you can see, the values in the darker shade of blue specify high correlation and in lighter shade specify the lower correlation. Using the CARS data set, we have found out the correlation matrix, which is the highest value that you see here. It is 0.95, which is the darkest shade of blue. So which belongs to displacement as well as the cylinders. So thus we can say that cylinders and displacements are the most correlated factors of our CARS data set. Thank you.
Thank you.
Keep looking for more interesting project on our channel. Thank you.